Dear students of the software engineering class, in the last chapter we have discussed the design as a general concept, and then we have studied the details of the architectural design. In this chapter we will discuss the distributed system design. Starting back at the second half of the 1980s, with the emergence of the computer networks, distributed systems have become a design option for system and software engineering. Virtually all large computer-based systems are now distributed systems. Information processing is distributed over several computers rather than confined to a single machine, and distributed software engineering is therefore a very important engineering option for enterprise computing systems. With the appearance of the distributed systems as design alternatives in software engineering, now software engineers have to study the characteristics of distributed systems. Among others, resource sharing, openness, concurrency, scalability, and fault tolerance are important distributed system characteristics. The resource sharing ability of a distributed system shows how it allows the sharing of hardware and software resources that are associated with computers on a network. The openness property of the distributed systems show that they are designed around standard protocols that allow equipment and software from different vendors to be combined. The concurrency property of distributed systems imposes that distributed systems may operate at the same time on separate computers on a network. These processes may but need not communicate with each other during their normal operation. The scalability property implies that a distributed system capability should be increasable by adding new resources to cope with the new demands on the system. In practice, the network linking the individual computers in the system may limit the system scalability. And finally, fault tolerance implies that the availability of several computers and the possibility that the same software routines may exist in a multiplicity means that distributed systems can be tolerant of some hardware and software failures. Distributed system disadvantages are complexity, security, manageability, and unpredictability. The distributed systems are more complex than centralized systems because there are a number of processors on which there is a multiple number of processes that run, and there is a middleware, there is a network on which the communication of these processes is based upon. With these components that compose the distributed systems in mind, we will understand that it is harder to comprehend the emergent properties and to test these systems. For example, rather than the performance of the system being dependent on the execution speed of one processor, now it is dependent upon the network bandwidth on which the processors communicate, plus each individual processor's performance. Further, moving resources from one part of the system to another, we can also radically change the system's performance. Now that the distributed system runs with a multiple number of processes on a multiplicity of processors, and since they need to communicate with each other, there will be a traffic on the network which connects them, and this will make the system, the distributed system, more vulnerable to external attacks. This makes the security more critical in distributed systems than single processor systems. About the manageability, more effort is required for system management for distributed systems because there may be different types of processors that run on the same system, and there may be different versions of an operating system at different processors. So to manage that would be a problem. Further, a problem that occurs in a processor or on the network may propagate to other process or other components of the distributed system, and these as an extra have to be managed in distributed systems. The unpredictability of the distributed systems originates from the fact that the network that connects the different components of a distributed system may be unpredictable in its response due to its load. And the network load is totally independent or uncontrollable by the distributed system. So that's why the distributed system is likely to provide unpredictable responses. We can name two groups of architectures for distributed systems. The first one is client-server architectures, where distributed services are provided by servers and requested and used by clients. And the second group is distributed object architectures. The difference of distributed object architectures from the client-server architectures is that there are no distinction between clients and servers. They can both provide and request and use services. The software medium through which the components of a distributed system can communicate with each other is called middleware. Middleware manages and supports different components of a distributed system. In a sense, it sits in the middle of the system. Middleware is usually off-the-shelf rather than specialist written software. That means you can buy it from the market, readily available. Transaction processing monitors, data converters, and communication controllers are examples to middleware. Now we will look into several distributed system architectures. The first one that we will study is the multiprocessor architectures. These are the simplest distributed system models where they're composed of multiple processes which usually run on different processors. Multiprocessor architectures are the model of many large real-time systems. They have a process-to-processor distribution where the order of the run is either pre-ordered or they're under the control of a dispatcher. An example to multiprocessor architectures you have seen in the previous chapter when we studied the computer-controlled insulin pump. Here you can see an example to multiprocessor systems. This is a traffic control system. There are three processes that make up the distributed software system. At the very left, you can see traffic flow sensors and cameras which serve as input units to sensor processor. The sensor processor receives this information gathered by the traffic flow sensors and cameras, and they send it after the necessary conversions to the display process. The display process makes this information available to the operator consoles and transmits it further to the light control process. The light control process is responsible for processing this information taken from the sensors and computing the necessary time for the red and green and red lights, and to send this information to the output units, which are the traffic lights, and these lights this way try to control the traffic as efficient as possible. Another distributed system architecture type is client-server architectures. They are modeled as a set of services which are provided by the servers and a set of clients that use these services. In this architectural style, clients are aware of servers, but servers do not know of clients. Here what we mean by clients and servers are logical processes. They are resided or located on processors, but the mapping of processors to processes need not be one-to-one. Here you can see a sample client-server system with server processes shown in rectangles and client processes shown in circles. And here you can see the processor-to-process distribution of the client-server system from the previous slide. As you can see, in the server computer 1, the third and fourth server processes run, and in the second server computer, S1 and S2 are run. And as shown in the diagram, there are 6 client computers, and the distribution of the client processes on these computers are as shown in the diagram. Another architecture type for distributed systems is the layered application architecture. In this type of architecture, we can distinguish between 3 different layers. The first one, that is closest to the user, is the presentation layer. It presents the results of a computation to users, and it collects user inputs. Another layer is the application processing layer. It is connected to the presentation layer. It provides application-specific functionality in a banking system, banking functions such as open account, close accounts, etc. It is, as I said, connected to the presentation layer for sharing the inputs and outputs, and it is also connected to the data management layer, which is the third layer in the layered application architecture, which manages the system databases. Here you can see the connection topology of the 3 layers. Presentation layer receives the input from the user, it pre-processes it, validates it, and then communicates it with the application processing layer. Application logic in the application processing layer processes data accordingly, and if necessary, sends this data to the data management layer, or gets some data from the data management layer, again processes it, and then if necessary communicates again this new information with the presentation layer. And presentation layer shares it with the user if if the user expects some output. This slide has two essential functions. One, it shows how the information is encapsulated in this architecture. And two, it shows the idea that the information can be further encapsulated into more than 3 layers. In this slide, we will introduce the concepts thin and fat clients. Here the question is, how should we distribute the 3 layers, the presentation layer, the application processing layer, and the data management layer in client and server sites? When we think of having the presentation layer only at the client side and the application processing layer and the data management layer on the server, then we are talking about a thin client model. On the other hand, if we have the presentation layer and the application processing layer in the client side and the data management layer only at the server, then we're talking about a fat client model. And here you can see the diagram of both thin and fat clients. They both have their pluses and minuses. As you can see, the network, that is the middleware, is in between the presentation layer and the application processing layer in the thin client model, and in the fat client model, the middleware is between the application processing layer and the data management layer. Thin client model is a good approach to build a modern user interface for the legacy systems when the legacy systems are migrated to client and server architectures. The legacy system acts as a server in its own right with a graphical interface implemented on a client. A major disadvantage of thin client models is that the thin client model places a heavy processing load on both the server and the network. We said that in the thin client model, the server and the network is heavily loaded. So that means there is a degradation in the performance for thin client models. On the other hand, on fat client model, more processing is necessary at the client because the application processing layer is run by the client. So this is usually more suitable for new client server systems where the capabilities of the client system are a priori known. This is more complex than a thin client model. The fat client model is more complex than a thin client model, especially for management. And new versions of the applications have to be installed on all clients. That means while performance is a weak chain for the thin client model, for the fat client model, maintainability is a disadvantage, because when a change occurs in the software, then you have to install it in all clients. Here you can see an ATM system as a typical example to client server systems. ATM machines hold the client software, and at the account server we have the teleprocessing monitor and the customer account database. As you see, the customer account database is not directly connected to the ATM machines. There is a teleprocessing monitor in between, and what it does is it puts the transactions coming from the ATM machines into an order, and then it lets the customer account database in an order handle these transactions. That the customer account database handles the transactions in a serial order means that the system can recover from faults without corrupting the system data whenever necessary. Now let's discuss the client-server ATM system as a thin client system and a fat client system, and let's analyze these two versions of the ATM system from the viewpoint of different system properties. A thin client system, for example, with the processing layer, with the presentation layer at the ATM machines and the teleprocessing monitor and the customer account database both on the account server, places a heavy processing load on the network between the ATM machines and the teleprocessing monitor and on the account server on the server side, because two layers run on a single computer. So from the performance viewpoint, the thin client system is in bad shape. But from the maintainability viewpoint, it is good because whenever you change the system, either the application processing layer or the data management layer, you can install the changes right away only on the server side, and that would be it. From the security viewpoint, the thin client system is again fine because what we consider the critical information as the information between the teleprocessing monitor and the customer account database, it will be on the server. It will be both on the server side, that is on the same computer, and they will be not really open to a system breach. From the scalability viewpoint, the thin client system is again not good because whenever we need to add extra servers for the data management layer, we are going to have to make the necessary changes for the connection between the teleprocessing monitor and the customer account database, and that will be rather hard since they're on the same computer. Now let's look at the fat client ATM system. The teleprocessing monitor will be on the client side, that is, ATM machines will run the teleprocessing monitor, and whenever we need to make a change on the teleprocessing monitor, we're going to have to install it on all ATM machines on the client side. So this will be rather a cumbersome process. So from the maintainability viewpoint, fat client will not be in good shape. From the performance viewpoint, the fat client will be in a better shape because the heavy processing load will be shared between the server and the client side, because since the teleprocessing monitor will be on the client side, and the traffic between teleprocessing monitor and the data management layer will not be as heavy as the trafficking between the client side and the teleprocessing monitor. So from the performance viewpoint, the the fat client ATM system will be better. Looking at the fat client ATM system from the security viewpoint, since the critical information between the teleprocessing monitor and the customer account database will be on the network, FAT client will not be a secure system. So from the security viewpoint, the FAT client system will not be in good shape. FAT client ATM system will be fine on scalability because the customer account database will be the only component of the software on the server side. So in both versions of the client-server ATM system, we have pluses and minuses. The rather long discussion in the previous slide brings us to the following idea. What if we put the teleprocessing monitor into another computer and consider it a different layer? This question and this idea bring us to the concept of three-tier architectures. In a three-tier architecture, each of the application architecture layers may execute on a separate processor. Three-tier architectures allow for better performance than a thin client approach, and they are simpler to manage than a fat client approach. They also are a more scalable architecture. As demands increase, extra servers can be added on both application processing layer, as teleprocessing monitor on the ATM example, and the data management layer. This is the diagram of a three-tier client-server architecture, where, as you can see, the application processing is separated from the data management and shown in a standalone layer. Here you can see an internet banking system as an example to a three-tier client-server system. As you can see again in the diagram, the customer account database, that is the data management layer, is separated from the application processing layer, which is the account service provision. Here, at the account service provision, as we mentioned before, the requests, the transactions coming from the client is serialized into a sequence, and each transaction is handled separately in the customer account database. And in any case of a problem, database is not corrupt. In this slide, we study what type of architecture should be used for what type of applications. Thin client architecture should be used for legacy system applications where separating application processing and data management is impractical. These are applications where there's a software product used since years, and we want to add to those a modern user interface and run these applications using this interface. Here, it's not really a good idea to separate application processing and data management because they only need a modern user interface. Another example where we can use thin clients is computationally intensive applications such as compilers with little or no data management. Here, application processing is mostly taking time of the server side, and what we need to do is to add a user interface to the client side. Another example, another application type rather, where we can run thin clients is data intensive applications with little or no application processing. These are also good for thin clients to use. Where we can use fat client architecture is applications where application processing is provided by off-the-shelf software on the client. So here, adding the application processing to the client side won't harm the system. Another application type where we can finally use fat clients is computationally intensive processing of data is required. Data visualization is an example to such applications. Also, applications with relatively stable end-user functionality used in an environment with well-established system management is good for use of fat clients. And finally, three-tier or multi-tier client-server architectures are good to use in large-scale applications with hundreds or thousands of clients, or in applications where both the data and the application are volatile, and finally in applications where the data from multiple sources are integrated. In the client-server architecture style, client is the software component that requested services, and servers are the software components that provided these services. In the distributed object architectures, there is no distinction between clients and servers. Each entity in the distributed software is an object that provides services to other objects and receives services from other objects. So each object adopts both roles of the client and the server in the distributed object architecture. Again, as in the client-server architecture, there is a middleware that provides the communication of objects. The middleware in the distributed object architectures is called Object Request Broker. However, the distributed object architectures are more complex to design than client-server systems. As you can see in this slide, there are objects distributed on a system, and there's an object request broker that is the middleware of the system that provides a seamless communication between these objects. Well, this architecture removes the distinction between clients and servers. An object may provide a service that is requested by another object, and the objects do this without any logical distinction between a client and a server. And the magic hand that manages this is the object request broker. It provides a set of services that allow objects to communicate and to be added to and removed from the system. In this slide, we discuss the advantages of distributed object architecture. The distributed object architecture allows the system designer to delay decisions on where and how services should be provided. Unlike in the client-server system, that can be done because each object in this architecture style is homogeneous, so they can all take over the role of a client or of a server. Thanks to this, unlike the system designers of a client-server architecture, the system designers using distributed object architectures can delay their design decisions about which objects should provide which services. Another advantage is that it is a very open system architecture. Distributed object architectures allow new resources to be added to the architecture as required. Thanks to the Object Request Broker, object communication standards have been developed and implemented that allow objects written in different programming languages to communicate and to provide services to each other. Maybe the most striking advantage of distributed object architectures is that they're flexible and scalable. Different copies of the system with the same service provided by different objects or by replicated objects can be created to cope with different system loads. This way, new objects can be added as the load on the system increases without disrupting other system objects. And another advantage of distributed object architectures that they are dynamically reconfigurable with objects migrating across the network as required. This is an important feature for distributed systems where levels of requests on services are dynamic. For example, a service providing object can migrate to the same processor as service requesting objects, thus improving the performance of the system. You can use a distributed object architecture in two alternative ways. You can either use it as a logical model, allowing to structure and organize the system. In this case, you think about how to provide application functionality in terms of services and combinations of services. Then you have to think of how to provide these services using a number of distributed objects. At this level, the objects you design are usually rather larger objects that provide domain-specific services. For example, in the packing robot control system in the architectural design, these large grain objects may be portions of subsystems such as packaging selection system or packing system or arm controller or gripper controller from the arm control subsystem. Another example, in a retail application, there may be large grain objects concerned with stock control, customer communication, goods ordering, and so on. The alternative use of distributed object architectures is as a flexible approach to the implementation of client-server systems. The logical model of the system is a client-server model in this case, but both clients and servers are realized as distributed objects communicating through a common communication framework. Here you see an example to the distributed object architecture. This is a data mining system. At the left-hand side there are various databases. In the middle there are integrator objects, and at the rightmost column we have various function modules. You may think of this data mining application as one that mines data in a retail business, which has food stores and hardware stores, for example, and wants to find the relationships between a customer's food and hardware purchases. For example, male customers may buy diapers along with some beers and chips, especially right before the times of football games. Finding such a relationship, the retail store may target the diaper customers and beer and chips customers right before the football games, and that would be a good sale for them then. On this slide, each database can be encapsulated as a distributed object with an interface that provides read-only access to its data. Integrator objects are each associated with specific types of relationships, and they collect information from all of the databases to try to extract relationships. There might be an integrator object, for example, that is concerned with seasonal variations in goods sold, and another that is concerned with relationships between different types of goods. And at the rightmost column, there are a number of objects that can produce outputs about these relationships in different formats, as a report or a visualizer or in some other type of display. Visualizer objects, for example, interact with integrator objects to produce a visualization or a report on the relationships that have been discovered. Because of the large volumes of the data that are handled, visualizer objects will normally use graphical presentations of the relationships. Several further remarks about the data mining system. The logical model of the data mining system is not one where the services are pre-specified. The second remark is that it allows the number of databases that are accessed to be increased without changing or disrupting the system. And the third remark is that it allows new types of relationship to be mined by adding new integrator objects. In all these remarks, you can see that the data mining system is flexible and scalable. Starting from that point, we will discuss a middleware standard for the distributed object architectures. CORBA stands for Common Object Request Broker Architecture. It is a standard for an object request broker, and it organizes communications between distributed objects. Assuming that the different objects in a distributed system may be implemented using different programming languages and on different platforms, CORBA has to do a lot to fulfill its job. And that's why the distributed object architectures are complex, more complex to implement than client-server architectures. Middleware for distributed computing is required at two levels, at the logical communication level and at the component level. At the logical communication level, the middleware allows objects on different computers to exchange data and control information. With this property, CORBA provides for the platform independence in distributed object architectures. At the component level, the middleware provides a basis for developing compatible components. CORBA components standards have been defined. CORBA standards, defined by the Object Management Group, or OMG in short, state the principles of object-oriented development. In this slide, you see of what components, as OMG sees it, a distributed system should be made up. Application objects designed and implemented for this application Domain facilities defined by the OMG for a specific domain. Fundamental CORBA services that provide basic distributed computing services such as directories and security management. And horizontal CORBA facilities such as user interface facilities, system management facilities, and so on. Horizontal facilities here suggests that these facilities are common to many application domains, and the facilities are therefore used in many different applications. You may think of CORBA services as facilities that are likely to be required by many different distributed systems. Among as many as 15 common services, some examples are naming service, for example, and trading service. These services allow objects to refer to and discover other objects on the network. The naming service is a directory service that allows objects to be named and discovered by other objects. This is like the white pages of a phone directory. The trading services are like the yellow pages. Objects can find out what other objects have registered with the trader service and can access the specification of these objects. Horizontal CORBA facilities are general purpose components such as user interface components that are common to many application domains, and unlike object services, they are oriented towards end user applications, which are called, as opposed to horizontal CORBA common facilities, vertical CORBA components. Example to horizontal CORBA facilities are distributed document component facility, DDCF, a compound document common facility based on OpenDoc. DDCF allows for presentation and interchange of objects based on a document model, for example, facilitating the linking of a spreadsheet object into a report document. At the beginning, distributed computing was mostly implemented at an organizational level due to security and interoperability reasons. This way, the computational load could easily be distributed among the servers of the organization, and local standards of the organization can be applied easily. And for web-based systems, where there are components of the system that access to the organization's servers from outside, we're running only user interface software. But now, inter-organizational distributed computing models are also available. So, this way, we are discussing another type of architectures. These are inter-organizational distributed computing architectures. There are two different types of architectures available in inter-organizational distributed computing architectures. These are peer-to-peer computing systems and service-oriented systems. Peer-to-peer computing systems are based upon the realization of computations by an individual network of nodes. On the other hand, service-oriented systems rely on distributed services rather than distributed objects, and they further rely on XML-based standards for data exchange. Peer-to-peer systems are decentralized systems where computations may be carried out by any node in the network. That explains the fault tolerance feature of the peer-to-peer systems, where any function can be run in many nodes of the networks. The overall system is designed to take advantage of the computational power and storage of a large number of networked computers. Most peer-to-peer systems have been personal systems but there is increasing business use of this technology. Some examples to peer-to-peer architectures are file sharing systems on PCs, instant messaging systems such as ICQ to establish a direct communication between users. The model of the peer-to-peer architectures can be studied in two different levels. The first level may be the logical network level, and the second level may be the application architecture. In the logical network level, we see that peer-to-peer architectures are decentralized architectures, and their advantage is that they're fault tolerant, and their disadvantage is that the peer communication overhead is high. To avoid this overhead to some extent, another logical network architecture is proposed, and this is semi-centralized architecture. Here some nodes act as servers to facilitate node communications. And at the application architecture level, the generic organization of components making up a peer-to-peer application. That is what we see in the application architecture level. Here you see a typical decentralized peer-to-peer architecture. Many nodes are connected to many others. This way, there's a high redundancy in peer-to-peer decentralized architectures, and this results in there being fault tolerant and tolerant of nodes disconnecting from the network. But for the same reason, there are also obvious overheads in the system in the way that the same search may be processed by many different nodes, and there is significant overhead in replicated peer communications. Well, to solve this to some extent, semi-centralized architectures are proposed. Here you see a typical semi-centralized peer-to-peer architecture. In a semi-centralized architecture, the role of a server is to help establish contact between peers in the network or to coordinate the result of a computation. For example, if this diagram represents an instant messaging system, then the network nodes communicate with the server to find out what other nodes are available. Once these are discovered, direct communications can be established and the connection to the server is unnecessary. Therefore, nodes N2, N3, N5, and N6 are in direct communication. The development of World Wide Web systems means that access is possible of clients to remote servers, provided that the servers keep information in HTML format. The problem here is that the HTML-only access is not practical. That means opportunistic connections between servers where a program performs a search within a number of catalogs is not possible. The solution to that problem is web services, where organizations that want to make their information accessible to other programs can do so by defining and publishing a web service interface. This interface defines the data available and how it can be accessed. The essence of web services is twofold. Service provided is independent from the application using the service, and the service provider may offer specialized services, and any service user can use it using a standard programming language or a specialized one. This is how a web service works. A service provider offers a service by defining its interface and implementing its functionality. A service requester binds that service into its application by including code to call that service and process the results of the service call. Service provider makes an entry what the service does and how it is accessed in a service registry to ensure the access of service by external users. And this is the diagram of the web service as explained in the previous slide, how it works. With the discussion of the service-oriented architectures, we conclude the distributed system architecture.